is systems engineering really engineering? I don't have answers. I'm just asking a lot of questions. But this is really a rhetorical question, and of course what I mean by that is how do we make sure that systems engineering is engineering? What do we need to do to make sure it lives up to the requirements of the discipline of engineering? And by the way, you can see from my bio that I'm not trained as a systems engineer. I'm trained as an applied mathematician and electrical engineer. So, you know, I sort of bring this perspective of what differentiates this field from the ones I was trained in. And I'm the kind of person who likes to do annoying things like go back and ask, you know, what are the fundamentals here? What's really important? And are we respecting the key principles? Not just are we doing things because that's the way we do. So anyway, if we want to make sure systems engineering really is engineering, then we need to talk about what engineering is. And that's really a big job, and it's more for philosophers than engineers, and I don't want to try to define engineering, but we can talk about what are some of the things that engineers do, and what does it mean to do those well. So I'm going to start out by talking about two complementary things that engineers do. And I'm not trying to say these are the only things they do, but these are key things engineers do. And they're part of the heart of what we do and part of what we need to do well. So one is they describe the world, not only as it is, but as we imagine it to be. A design for a system, say a space vehicle, is really a description of the world the way we imagine it could be, right? If we just have the design, but the vehicle doesn't exist yet, we're really sort of describing, well, what will the world be like if we had such a vehicle? We also describe the way the world is. We talk about the problems we have. You know, engineers solve all kinds of problems like there's water here and we don't want there to be water here, or there's valuable materials here and we want to put them somewhere else, or there's a message here and we need to deliver it to someone far away. These descriptions of the world and our problems in it are also, as I said, descriptions of the world. So we have to talk about what the world is like and what we envision it to be, because we're problem solvers. In addition to that, and part of what distinguishes engineering from just, say, science fiction, is that we do analysis of these descriptions, and we try to connect a design with its consequences, the sort of forward implication problem. You say, well, if we design the vehicle in this way, how much capacity could it carry? How fast could it go? What orbit could it achieve? And those are interesting problems that require a lot of physics and math, but the really more interesting problems is if you want to carry a payload this massive to this orbit, what kind of design do you need? The sort of inverse problem. And all of these involve analysis. And in particular, they typically involve science and math to do rigorous analysis. In general, you don't succeed as an engineer if you say, well, I just thought about this really hard and I really believe it will work, right? That's usually not enough. Usually you have to do some math or analysis to say, we have high confidence that this design will achieve the state of the world that we are seeking, and we use science to do that. And I think the word rigor here is very important. It's one of my favorite concepts, although I think it's widely misused. So I'm going to talk a little bit about what do I mean by rigor. There's two definitions I like. One is just the standard dictionary definition, the quality or state of being very exact, careful, or strict. That is, in general, a virtue. Obviously, like all virtues, you can overdo it, but that's something I think we aspire to as engineers. We do try to be careful. We do try to be exact. We do try to be strict. We don't assume the laws of physics will bend to our will just because it would be convenient. Another definition or characterization of rigor that I really like is the NASA final report of the Return to Flight Task Group. I may have that wrong. I think it's Annex A2. But anyway, that document is online, and that annex or appendix is a beautiful essay on the importance of rigor and the importance of modeling. And they define rigor as scrupulous adherence to established standards for the conduct of work. And I like that a lot. I think we need standards, not the sort of uninteresting but useful kind of standards like, you know, RS 422, but I mean standards that say the work that doesn't achieve this level of quality is not considered good enough. And that means sort of checking your work and evaluating the error bounds and applying due diligence and having good reviews and all the things we need to do to make sure work is good. So those are sort of some introductory thoughts about what characterizes the practice of engineering, and let's now look at that in a little more detail. So this is my little speech about rigor. I think it's a distinguishing virtue of engineering. It's what we do. There's no choice about being rigorous, in my opinion. It doesn't require a justification, and I don't offer any. But rigorous does not mean detailed. It doesn't mean you model the behavior of a space vehicle down to individual, atoms. That's not what rigorous means. It means you model down to the level that is important for the things you care about, and you can justify not going further. And it's not too hard to justify why we don't need to model down to the behavior of individual atoms if what we're really trying to figure out is, can we loft the payload into a certain orbit? So, people often really get hung up on this word rigor, and they think it means, never stopping. It doesn't mean that at all. It means knowing where to stop and why. And it's not a value to be traded against time or money. It doesn't make sense to say, well, we don't have time or money to be rigorous. In particular, rigor is what tells you where to save time and where to save money. It tells you when it's safe to make simplifications or take shortcuts or to neglect second or third order effects. It's exactly what you need when you've got limited time and money. And it benefits everything, simple and complex. Keep going here, large and small. It helps you understand your mission objectives and their constraints better. It helps you describe more precisely your designs and their realizations. And it helps you do more thorough and principled verification and validation. It helps you find defects earlier and fix them. And it helps you make more accurate projections or predictions of how much it will cost and how long it will take. So it's really a very important arrow in our quiver. And my opinion is that engineers ought to be all about rigor all the time. I'm getting some echo here, so maybe somebody needs to mute. So where do we find rigor in engineering? Well, I think it primarily appears in three places. One is we use precise language to describe things. And I'm going to go into more detail about all of these. But we don't just sort of write impressionist poetry to describe a bridge. We describe the bridge in terms of its structural elements and their relation to each other. And we use words like, tension and compression and span and strut and I-beam and words that are meaningful. So we use precise language when we describe things. We use mathematical abstractions to analyze things. I kind of think that goes without saying, but I'm going to make a few points about sometimes these abstractions come from places that we don't expect. or they should anyway. And we use automation to do both of these things. So if you put all that together, you get this really sad little diagram. And I'm going to show my cursor here just for a second. The key idea is connecting designs and consequences, right? This is when I said we analyze the state of the world as it is and as we imagine it to be. So we use language to describe designs, and we use language to describe consequences. This language might be figures of merit or requirements or constraints. This language might be, compositional structures of things or software or, design parameters. And we connect those with analysis, which makes heavy use of mathematical abstractions and, in the modern world, automation. So I'm just going to talk a little bit more about all of these things, language, abstractions, and automation. And then we'll sort of come back around and say, what does all that mean for systems engineering? So let's talk a little bit about language. Well, we can't analyze what we can't describe. I think that's obvious, and we can't describe precisely without precise language. And if you look at the practice of mature engineering disciplines, they have lots of terms for describing things, and they're often in taxonomic relationships. So in electrical, for example, we see things like resistor, capacitor, filter, amplifier, and there's lots of, taxonomies. There are types of filters, like or types of capacitors. Say there's electrolytics and disc, etc. So we have these taxonomies of things, and we're more or less precise about what they mean. And in particular, we know that when we say capacitor, we don't mean amplifier, and vice versa. That these are distinct concepts. Mature disciplines also now take these vocabularies and develop grammars for making, sentences out of the vocabulary. So if you look at, say, SPICE, which is a language for describing circuits, and in particular for the purpose of simulating or analyzing them, the SPICE net list is essentially a set of sentences whose words have things like resistor, capacitor, etc. in it, but they're now into sentences like this terminal of this resistor is connected to this terminal of this resistor, and that terminal of that capacitor is connected to this terminal of the input, etc. And again, this language has rules, so we know that it doesn't make sense. Unless we're talking about a variable resistor, we know it doesn't make sense to bond the lead of one circuit element to the middle of a resistor, right? We always connect to one end or the other. So that's a grammar rule that tells us whether these sentences are well formed or not. So what do precise languages in general look like? Well, they generally have vocabulary. They have syntax, that is, rules for constructing sentences that tell you whether something is legal or not. And they also have semantics, which is meaning in the real world. We don't just describe circuits for the amusement of doing it. We describe it because we want to talk about the behavior of the circuit, and that's what semantics is. It's what does this mean in the real world? And to engineers, real world meaning comes from analysis. That's the method we use to predict what, or to describe what happens in the real world or predict it. In particular, we analyze. And that really brings us to abstraction. Abstractions are essentially how we do analysis, and I'll give you an example. So again, from electrical engineering, if you look at the EE 101 textbooks, they'll talk about RC circuits, and they'll tell you that an RC circuit can be modeled by a simple linear ODE. Now, we know that's an abstraction. We know it's an idealization, that a real RC circuit in the real world does not have these beautiful linear, time invariant, temperature invariant properties, right? We know that this is an idealization, but we can do useful things with it. In particular, we can solve it. We can give the solution to that equation, and we can say, this is how the circuit actually performs. And the only reason that's useful is even though that abstraction is imprecise, for many purposes, the predictions it entails are close enough to the actual behavior that we can use it in the real world, not only to say this circuit behaves like that, but even more, we can say, we can say, well, how do we design a circuit? Sorry, I got to catch up here. How do we design a circuit so that it behaves the way we want it to be? So again, this is a case where the mathematical abstraction of a linear first-order ordinary differential equation is intimately connected to our job because this is part of the analytical machinery that we use to solve problems. And again, mathematical analysis is kind of what makes it engineering. There's nothing wrong with poetry, but it's not the same kind of activity. And in the same way, I wouldn't necessarily ask an electrical engineer to write a sonnet. I wouldn't ask a poet to design a filter. Now, what's interesting to me is the scope of the applicable math has enlarged over time. All engineers are very comfortable with the idea that calculus and linear algebra, differential equations, probability, those are all applicable to our work, and nobody really, I think, questions that. But there's a lot more abstractions that are becoming more and more pertinent to the practice of engineering, and I would include all these in these a bunch of discrete math things like formal logic, graph theory, abstract algebra. My favorite example of this is the Reed-Solomon code, which is an extremely practical discovery and is in every cell phone and practically every digital communications device in the world. But it's based on a mathematical abstraction that no one thought had any utility at all until the 20th century, namely 255-degree polynomials. I mean, algebraists proudly bragged that those were useless until Reed and Solomon came along and said, you can solve a lot of really practical problems with that. So the point of all of this is, I think as engineers, we always have to be alert to math that's outside of our comfort zone that may be useful for solving problems. And I think that's particularly pertinent to systems engineering, and we'll get to that in a minute. So now, language and abstraction actually go together very closely. Sorry, I can't back up. I just got to stop doing that. So if I ask you what is a capacitor, the image that pops into your head may very well be it's a little thing with two wires, and it might be shaped like a cylinder, or it might be flat. But I don't think a capacitor is necessarily a discrete component like that. In a way, a better definition of a capacitor is something that exhibits capacitance. And I know this sounds like a circular definition, but it isn't. Because we can say exactly what capacitance is. Capacitance is a specific analytical relationship between voltage and current, namely I equals C dV dt. And what we really mean, I think, is something is a capacitor if and only if it displays or it manifests this particular relationship. And by this definition, sometimes things are capacitors when we didn't intend for them to be, like, stray capacitance in a circuit. Well, we might not have put it there on purpose, but if it's there, we need to account for it. And so we can say, essentially, that there is a capacitor here because there's capacitance. Another example is touch screens. Some touchscreen technologies work because your finger will work like a capacitor, but it wasn't designed to be, but it exhibits capacitance. And I think that's true of engineering language in general. And the key idea is when we say something, it has known and direct analytical consequences, right? If I say something is a capacitor, then you immediately know, at least in the scope of that thing, I equals C dV dt. And it turns out if you look at almost any of the precise words, you know, names of things in any engineering discipline, but electrical, for example, the same thing. You know, a transistor is not just a thing with 3 wires on it. And it's a device that exhibits a kind of behavior, and there are different kinds of behaviors, and these are different kinds of transistors. You know, FETs are different from you know, the audio amplifier transistors, but what differentiates them is their behavior. A Butterworth filter is another example. The Butterworth filter is a famous sort of synthetic design solution to a celebrated problem, but what distinguishes the Butterworth filter from other designs is not its structure or any of its other properties. What really distinguishes it has a particular desirable behavior, namely it's maximally flat in the passband. The Reed-Solomon code, again, you can describe it structurally, but what distinguishes the Reed-Solomon code and what makes it interesting to us is this property of being the best linear block error correcting code of a given size. That is, its analytical consequences. If you employ the Reed-Solomon code, you can say with certainty that the error correction will behave in a certain way because that's the consequence of that design. So I think this, you know, relationship between abstractions and language is key. Languages shape abstractions and vice versa. So you look at some other examples. If any of you are familiar with this language Modelica, it's a language for modeling, and it's built around this abstraction of systems of differential algebraic equations. So anything that can be described as a system of differential algebraic equations has a Modelica representation, and vice versa. The language goes with the abstractions. Okay, a few words about automation. Another area where I think we just haven't thought as clearly as we need to is automation. And if you ask people why do we automate, they will almost always say because it saves time and money. And it may save time and money, but I don't think that's why we do it. I think we do it primarily because computers are really good for achieving rigor. They are really good at scrupulous adherence to whatever, right? If you write your software to do something and you do it well, the machines will not deviate from that. They won't get tired. They won't get distracted. They won't develop resentment over how little they're paid. They'll just keep doing what they do. And if we encode our instructions to the automatons, if we encode into that high standards for the conduct of work, then the computers will scrupulously adhere to that. That's why we can use them to save time and money, because we can rely on them to adhere to what we ask them to do. And if we ask our computers to do things that don't adhere to high standards, then we find that they can, you know, produce crap at a staggering rate, and we don't save any time or money. So I think they're useful precisely because they're really good at maintaining rigor. And it turns out automation has a lot of abstractions that are sort of pertinent to it, like algorithms and data structures. And a lot of these abstractions can be mapped to the abstractions of engineering analysis. So, for example, the notion of transitive closure is very much akin to the engineering notion of failure propagation, right? Failure propagation is sort of, can you reach here from there? And that's exactly what the transitive closure algorithm is all about. And there's lots of other examples, right? I mean, there's numerical algorithms for solving large linear systems are extremely useful for doing thermal analysis, for example, because we can pose, say, steady state temperature distribution problems as large systems of linear equations, and then we've essentially translated an engineering abstraction into a computing abstraction, and now we can automate the solution. So automation is really fundamental to machine engineering, to modern engineering, because well-defined languages, I don't mean computer languages, I mean engineering languages are amenable to machine parsing, like SPICE, like Modelica. And lots of useful mathematical abstractions and analyses are already out there in software libraries. And so we can solve the forward problems of saying, well, if this is our design, how will it behave? Sometimes by just brute force or perhaps more clever computing. But we can even go back the other way and say, well, if this is the behavior we want, what sort of system do we need to design? And there's lots of examples of that. You know, in mechanical engineering, there's lots of things that can tell you if you've got a beam and you can describe the load on it and you can describe the maximum deflection you want, and it's, you know, its length and all whatever else goes into the computation, it can tell you how big a beam and what, you know, material you need to achieve that. Same thing with electronics. If you need a filter that behaves in a certain way, there's algorithms that will design the filter to do that for you. And automation is really important for all of those kinds of things. So that's a few words about these three important topics: language, abstraction, automation. And now I want to talk a little bit about, well, how do those apply to systems engineering? So let's go back and talk about, you know, is the practice of system engineering rigorous? Do we use precise language? Do we employ abstractions well? Do we automate effectively? And how can we do better? So systems engineering language. I think it's fair to say that we have a lot of distinct concepts in systems engineering. We talk about components and functions and interfaces and requirements and risk and constraints and all sorts of things. But I don't think we have reached sort of discipline-wide agreement about what are the proper uses of those words. I think we have a lot of local conventions that are not discipline-wide. For example, we get hung up all the time on what is a subsystem of JPL, because there's really two very distinct ways of thinking about a subsystem. And the textbooks, in my opinion, gloss over this. So these are things that I think we need to struggle with. But in general, I would say as a discipline, we lack agreement on names for fundamental things, like we use the word component like for elements of a product breakdown structure. And we just stole that from Core, and they stole it from RDD 100, and who knows how far back that goes. But some people don't like that word, and some people use some other word instead. The word itself isn't as important as reaching agreement on what word to use, and I don't think we have any sort of discipline-wide agreement. We haven't really agreed on the names of properties of things. You know, you could say, you know, the ISO 80,000 standard or the Bureau of Metrology standards are good for describing properties that are quantities like mass or, you know, length, but we don't necessarily have agreement on how we talk about identifiers for things or, you know, qualitative attributions. And we haven't really got precise, we haven't got agreement on precise language for how do we talk about a relationship between a component and a function. You know, the word performs is sort of an obvious candidate for that. But again, I don't think the discipline has settled on terminology here. And then, even more than that, we need to talk about semantics. So if we said it's legal to say a component performs a function, one of the things you'd need to ask is it meaningful to say a function is performed by more than one component? obviously a component, I think it makes sense to say a component can perform more than one function. But if you say a function can be performed by more than one component, you're introducing ambiguity now. And if you can live with that, fine. But if you don't want to live with that, then maybe you want a grammatical rule that says function is performed by at most one component. And again, I have a preference for what the answer should be, but my main point here is that we as a discipline haven't reached consensus on an answer. I'm not even sure we even recognize it's an important question yet. So how can we do better? Well, I think in this case, it's kind of a no-brainer. There's a very well-established field of theory, practice, and technology out in the world today that's about the precise representation of knowledge, and they call it knowledge representation. It's a branch of computer science, and it's really quite mature, and they've got lots of tools and theory and software, a lot of which is embodied in this practical project called Semantic Web. And I think we as a discipline could use these tools, and in particular the tools of the Semantic Web, to build communities of consensus around system engineering language that we capture in formal ontologies, which is exactly where we would put those rules, like, is it legal to say function is performed by more than one component? But the main purpose of doing this is to inform the way we talk to each other. I mean, it would be important to put this agreement on words and their meaning into tools and software, but I think even more importantly is for human communication, and in exactly the same way that you can take an electrical circuit diagram, say a full wave rectifier, filter, power supply design. You can take that anywhere in the world and show it to a qualified electrical engineer, and even if you don't speak a word of natural language in common, they will understand what is meant by that. And that's, I think, important for advancing as a discipline, that we need to agree on how we talk to each other. There's not any common way that I could describe a product breakdown structure to another system engineer and be confident that they would understand it in the way I mean it. We don't have language for even simple things like that. And we need to incorporate this consensus into tools and software, particularly SysML, and I'm very pleased to see that the SysML version 2 effort is moving very deliberately and intentionally toward a more semantically grounded language definition, and I'm supporting that effort in a somewhat unofficial way, but it's good news they're moving in that direction, and I applaud it. And every time I say this, it's controversial, but I don't think it should be. I think we need to reject ambiguity from our practices. And what I mean by that is being precise about uncertainty is good. Being ambiguous about anything is not. And the difference between those is saying, the temperature is within an order of magnitude of some point is a precise statement about uncertainty. I don't know the temperature, but I can tell you something about it. But if I just say it's pretty hot, that's ambiguous because you don't know what I mean by that. And so people get hung up on this because they think ambiguity is a property of the world. I don't think it is. And if you look it up in the dictionary, ambiguity is really a property of language. We don't want to say things whose meaning is unclear. We want to say things that are clear, but sometimes what we say is, my knowledge is uncertain. All right? I hope that's not a problem. But I think we can do a lot better as a discipline simply by taking the semantic web seriously and learning to use its tools to build language, to build consensus on language. So that's the first recommendation. Now, the second thing is about abstractions. And I think I would say that systems engineering doesn't really recognize a fundamental set of abstractions. I was trained as a control theorist And I was trained in a highly mathematical department, which is probably not the right place for me. But it became very clear that control theory, in its sort of rigorous origins, is grounded on functional analysis. Functional analysis is the study of mappings from functions to the real number line, and those real numbers are the figures of merits of controllers. And so if you want to say what's the best control algorithm to achieve this figure of merit, you're essentially solving a functional analysis optimization problem. And I think control theory as a discipline recognizes the importance of functional analysis as its sort of foundational theory. Now, part of the reason why systems engineering doesn't do that is the scope of systems engineering is so broad. There really isn't any simple set of abstractions like differential equations or functional analysis that covers the whole thing. We're really talking about everything, and that makes it challenging. But we can turn this broad scope a little to our advantage and say, well, what are we doing and what distinguishes that? Well, one of the things we have to do as system engineers is capture a diverse set of facts. We have to talk about environments, not only natural, but political and economic. We have to talk about structures of things. We have to talk about their behaviors. We have to talk about their interactions. We have to talk about uncertainty of design, risks, budgets, schedules. There's just hardly anything that's out of our scope. But capturing a diverse set of facts is very much in our wheelhouse, and relating diverse concepts to each other in a way system engineering is really all about relatedness. And I think there are abstractions that are directly targeted at these sorts of things, and I think the most important one is graph theory. And a graph in mathematics is simply a thing with nodes and edges, or vertices and edges, depending on whose terminology you're using. And the graph represents pairwise relations between objects. So a product breakdown structure is a graph. It's a particular kind of graph called a directed tree, but every object in that graph is described in terms of its relations with the parent thing that it's a part of and the things that are a part of it. And lots of things in systems engineering can be described with these sort of representations of relatedness. And it turns out that knowledge representation, the theoretical underpinnings, are also based on graph theory. So if we sort of understand the pertinence of these abstractions, it will dovetail nicely with our language, with our choice of language technology and theory, because they're all sort of based on graphs. And now we have a very natural connection between description of things. We describe things in terms of their relations to each other, and the analysis is graph theoretical operations on that, like finding cut sets and doing transitive closure, et cetera. So my recommendation would be that we really think seriously about expressing what we know about anything in terms of graphs, and then we can reason about whether the resulting graph is well formed according to the rules that we've decided on, and then we can reason about all kinds of degrees of relatedness. So we can say, what requirements does this requirement directly refine or indirectly? You know, that is just a reachability operation on a graph. And like I mentioned earlier, there's well-known sort of introduction to graph algorithms solutions that are directly pertinent to the sorts of engineering analysis that system engineers do. There's a legend, well, there's a treasured or famous or notorious anyway algorithm called connected components, and it helps you answer questions like, you know, are these faults isolated? If you do the connected components analysis and two faults are in different connected components, then there simply isn't a way for one to cause the other. Transitive closure I've always referred to. Root cause analysis is fundamentally a topological sort. So lots of these things that we're sort of comfortable with already, we can put on a little more rigorous mathematical basis, and then perhaps that will help us exploit automation better. And here's just a quick example of what it looks like to represent knowledge as a graph. And nobody should be surprised by this. You know, we all draw boxes and lines diagrams like this all the time. The only thing I would call your attention to on here is that this is not just a boxes and lines diagram. It is in fact a mathematical graph, because all of the nodes, all of the boxes have types. They have stereotypes applied to them. This is a SysML block definition diagram. And all the edges, all the relationships have types too. And so we can represent this as a knowledge representation graph, and we can reason about it. And the purpose of this particular example is to show sort of how a requirement for a data rate can be decomposed down into a requirement on transmitter power and a requirement on receiver sensitivity. And these two refinements of this requirement into these two child requirements is supported by some link margin analysis. And this tells us that these are related. And in particular, if we discover that our spacecraft is having trouble meeting this requirement, we know because of this analysis that we might have to go tighten this one up in order to get the same effective data rate. So, again, nothing new. It's just what we're used to on a little more rigorous, a little more formal basis. And then automation. I think automation is a particularly curious topic for systems engineering, because in the lifetime of the systems engineering discipline, certainly in my lifetime, computing has gone from a scarce, precious resource, very expensive, to something that's just bought in bulk. And when I was a young man, supercomputers were these exotic, amazing things. And now you can harness as much computing power as you can afford to air condition. The cost drivers now become engineering. The computing itself is almost done. The cost drivers become electrical power, energy, not computing per se. But I don't think we as a discipline have taken advantage of that. There are all kinds of analyses that are computationally intensive, like reasoning, like looking for inconsistency and unsatisfiability, search algorithms, planning and scheduling, which are kinds of search algorithms, feasible region bounding. There's all kinds of interesting problems in system engineering that we don't know how to attack with too much analytical cleverness, but we know how to just attack them with brute force computation. And I don't think we exploit that very well. I guess I jumped over the slide of that. But anyway, I think there are lots of areas where we could make use of high-performance computing and automation, and graph theory, again, helps us do that, because if we formulate our engineering problems as graph theory problems, then it's very well known how to solve a lot of graph theory problems with computing, and there's software written out there to do it. And so you just line up the machines on the Amazon, cloud and put them to work for you. So that brings me to the last chart, and I'll just make a few closing remarks. I think systems engineering is not necessarily engineering. It is engineering only to the degree that it achieves rigor. I got a little, this word through should not be there. I guess I shouldn't brag about rigor here, and I didn't catch my own grammatical errors. It achieves rigor in description analysis through precise language with rules and meaning, mathematical abstractions, and automation. I think if any field does that, it's engineering, and the same is true of systems. I think graph theory is a fundamentally applicable abstraction that is really important for both description and analysis, and therefore it empowers automation as well. And just finally, I'll just say a couple of words about this term model-based system engineering. I really detest this term, and I almost never use it except to complain about it, because it gets us thinking about the wrong thing, which is what is a model, and how is model-based system engineering different from whatever we did before? And I maintain it is not. It is not at all different in kind. It's different in degree. All engineering has always been model-based. The only difference is the content of the models is changing and the way we represent them is changing. We're all familiar with modeling differential equations, and no one questions that. The only thing different now is we're modeling different things. We're modeling discrete relations, the things that look like graph theory, and we're using automation more effectively, what we were always modeling. And so I would describe the MBSE as practice that achieves rigor through the use of, again, precise language, mathematical abstractions, and effective automation. If you're doing that, you're doing engineering. If not, then I don't think you're doing engineering. So like I say, I don't think model-based adds anything. I think all engineering that's worthy of the term makes use of models, because precise language with mathematical abstractions are models.